let's do an example and see if we can actually stick it all together and figure out what's going on. So here's a matrix which I'd like to find the inverse of. And as I said previously, the first step that I would do is to find the matrix of cofactors. So all I'm going to do is, for each element of this, I'm going to work out its cofactor. Remembering that for the cofactors, I need to bear in mind the place signs. So just put the place signs in so I don't forget. Okay, so starting in the top left, cross out the first row in the column, I'm left with 4. Take away -1 is 5, and it's positive. The next one is going to be 4. Take away 3 is 1, and it's negative. And the next one is -2. Take away 6 is -8, and it stays the same sign. What have we got here? We've got 2. Take away -1 is 3, and it's negative. And you can carry on and just check that I've got the rest of them right. I think you'll find it comes out to be that. Okay, so there's the matrix of cofactors. And now, the smart thing to do now is to pick the row with the greatest number of zeros and use that to work out the determinant. So I would say the row with the greatest number of zeros is the bottom row. So the determinant of A is just going to be 3 times -1 plus -1 times 1 plus 2 lots of 0, which is -3. Take away another 1 is -4. So we've worked out the determinant from the matrix of cofactors. So what you're doing is you're multiplying the original elements by their cofactors to get the determinant. And if you pick the one with the zeros in, it comes out the easiest. Okay, now we're on a roll because the adjoint matrix of A is just the transpose of the matrix of cofactors. So we take this matrix up here, turn the first row into the first column, the second row into the second column, the third row, into the third column, and that's our adjoint matrix. And then the inverse is just equal to 1 over the determinant, so 1 over -4, or -1/4, times the adjoint. Okay, and that should be the inverse of A. Okay, so it doesn't actually take that long to do it. And if I'm not telling you horrible lies, it should be the case that the inverse of A times A should come back to the identity matrix. So let's have a go at doing this. -1/4 times 5, -3, -1, -1, -1, 1, -8, 4, 0, times my original matrix A, which was 1, 1, 1, 2, 2, 1, 3, -1, 2. And if I multiply these things, I've still got -1/4. And what have I got? Row into column 5. Take away 6 is -1. Take away 3 is -4. 5. Take away 6 is -1. Plus 1 is 0. 5. Take away 3 is 2. Take away 2 is 0. And I'm fully confident if I keep on doing this, you can check it yourself, it'll all come out to be that, which is just the same as taking that -1/4 through gives me 1, 0, 0, 0, 1, 0, 0, 0, 1, which is indeed equal to the identity matrix. Okay, so I started with a particular matrix I was interested in. I found the matrix of cofactors. From that, it's very easy to find the determinant. The adjoint matrix is the matrix of cofactors transposed, and then the inverse is just 1 over the determinant times that adjoint matrix. And the verification of it that it all works is if you multiply your inverse matrix by your original matrix, you get back to the identity matrix. And that's all there is to finding the inverse of a matrix. A reasonably long process, but now that we've done it, we'll be able to use it, as we illustrated earlier, to solve systems of linear equations.